Good evening. Welcome to Chapter 8 in the ARRL Extra Class License Manual. We're going to be covering this chapter in two halves. We've got this week talking about modulation and protocols and modes. Next week we're going to be finishing up on that portion and be doing a section on amateur TV, which is kind of a niche area, but there are quite a number of pool questions, so we do need to cover it. And the technology is pretty fascinating as well. So I think you'll enjoy that. I always like to say, if we've got people out there watching us on YouTube that we don't know about, please let us know, especially if you're keeping current with with the current class, because we do have a YouTube mailing list that we send out notifications and sometimes attachments and links, so you'll want to be a part of that. That mail list only runs while the class is running, though, so if you join us 6 months down the road, that won't be something that would help you. All right, so let's jump right into it. So first of all, I'd just like to say thanks to some of the people that have helped us out here. ARRL, for sure, their license manual and a lot of their material. They allow us to use some of the graphics, and that's helpful. Dave Kassler, of course, has been wonderful, and he's given us permission to use his graphics, and you'll see a number of those tonight, and we've used them all through. And past students have been amazing. A lot of times we struggle trying to think of shortcuts, ways to remember some of the pool questions. And then what happens when we get those tips, we say, wow, that's a really cool thing. It winds up being incorporated into future classes. So yeah, we get help from a lot of sources. So thank you. So tonight we'll be covering these topics, as shown there. To just briefly put up this slide. It's on page 8-2 if it's kind of hard to read. But Dave Kassler goes through a little bit of discussion on the FCC emission designators. And back when I first became a ham in the late 60s, believe it or not, in our logbook we had to record this for every contact that we made, even if we called CQ and nobody answered us. That had to go in the logbook. So we had to use these emission designators as part of our log. That's all described a little bit further in the rules and regs. I gave a link here to Amazon for the FCC rules and regs. And this is something I'd recommend that you have a copy of because it has a few chapters in the beginning that are general and helpful in addition to the current rules and regs. So it's about $10. I'd recommend it. So, modulation systems. This is a fairly rich topic. So it's all about adding information to a carrier so that we can send it around the world. Going to be talking about these flavors of modulation. Just like to comment that frequency modulation and phase modulation are both forms of what are known as angle modulation. So in one of the pool questions, they reference angle modulation. If you can translate that in your mind to FM, it might be helpful. It's not something unique over and above the other two. So here we've got a picture. We've got an audio signal and an RF signal with the audio being combined with the RF to form amplitude modulation. This isn't to scale, of course. The frequency of the audio signal is very low, and of course if we showed a true representation of the RF, it would just be a solid black line. It's much, much higher. But you get the idea. The audio is superimposed on the carrier. And for AM, and then for FM, we start out with a carrier, and then we apply the audio signal to it, and you notice that it stretches out or compresses according to the signal being applied to it. So frequency modulation and phase modulation we introduced in a previous video, and just reinforcing those now. We're going to dig a little bit deeper into some of those topics this evening. It's interesting, AM was the first voice mode that we had in ham radio. It all started out with CW many, many years ago. And AM, of course, single sideband is a form of AM where we suppress the carrier in one of the sidebands. And even CW is considered a form of AM because with CW, you're turning a carrier on and off. With AM, you're always transmitting a carrier. So turning that on and off gives us CW. So quite a rich history there. Talking about frequency and phase modulation, just some preliminary information here. We're going to be varying the radio frequency, the RF frequency, from its steady state carrier frequency at the rate of the modulating signal frequency, which is audio. A little diagram up here. And the amount of frequency change is proportional to the modulating signal amplitude, which you could say is loudness. So the louder you talk, the further it's going to swing from its resting state. And that's called deviation. It's the amount that the signal deviates from that center frequency, related to loudness. There's something special about 29 megahertz that's going to be coming up. Just kind of seeding that thought for now. This whole section, some of it sounds pretty technical. There's a couple of definitions that we're going to need to know, and I spent quite a bit of time trying to figure out how to share some information to remember those definitions. We'll see if any of that helps. And then there's some calculation questions. They turn out to be extremely easy, though. So rest easy there. So here's a picture from Kessler, and I'd like to start off with is consider the modulating waveform. They're showing a sine wave here. And let's assume that we're applying a signal to the microphone input of our transceiver. It wouldn't be 1 volt, but let's just use that as a reference. So we're applying a 1 volt, 1,000 cycle sine wave to the input of our transceiver. And we're modulating, in this example, plus or minus 1.5 kilohertz. So here's the FM carrier frequency, and we're going to be going above and below that, 1,000 cycles per second, at a distance plus or minus 1.5 kilohertz from that resting frequency. If we double the modulating waveform loudness or amplitude, go from 1 volt to 2 volts, that's going to change the amount of deviation by a factor of 2. So instead of 1.5 kilohertz swing, we're going to a plus or minus 3 kilohertz swing. So the whole point of this slide is the louder the signal, the greater the deviation. Of course, there's limits on that because you typically don't want a FM transceiver to be deviating more than let's say 3 kilohertz or 5 kilohertz is what's pretty much the standard right now. So there's limiters built into the equipment to prevent it from going a lot higher. If it goes higher, then it winds up occupying more bandwidth and interfering with adjacent signals. So that's the concept. And then a bunch of technical sounding stuff. I'm going to show a definition for deviation ratio and modulation index and share some examples. And then I've got a slide that goes into a little bit more detail that I think will be helpful in remembering how these work. And I have highlighted a couple of words. So deviation ratio as a concept is the ratio of maximum carrier frequency deviation to the highest audio modulating frequency. So it's a ratio of 2 maximum frequencies. We've got the carrier frequency. How far are we going to deviate? And what is the highest audio modulating frequency? Well, highest would be, you could call that maximum. So it's really a ratio of 2 maximum frequencies, 1 RF and 1 audio. And whatever the deviation ratio happens to be, it's designed into the radio, and it's a constant for a given radio. So it'll be the same on any of the RF frequencies that you might be transmitting on. So this is just the introduction to the definition. And here's an example. There's 2 pool questions that ask a question similar to this. What is the deviation ratio of an FM phone signal having a maximum frequency swing of plus or minus 7.5 kilohertz if the maximum modulating frequency is 3.5 kilohertz audio? And it's really quite simple. It's the And it turns out to be the bigger number divided by the smaller number. Remember when we had op amps and we were calculating gain? Well, it's the same concept. It just works out that way, the way that they've constructed the pool questions. So you don't necessarily have to memorize this formula, although the formula works fine for this. Deviation maximum, that's here. Modulating frequency, maximum or highest modulating frequency, is here. Works out to 2.14. So here's an introduction to the definition and an example of a calculation problem. Now there's a couple of exam hints that I'll share. I already did one. Divide the bigger number by the smaller when it asks for a calculation. If you don't want to memorize the formula, which you're welcome to do that. And for all four of the calculations, no unit conversions are necessary. They'll either give it in hertz or kilohertz, so you don't have to worry about decimal points being off. And I ended with easy peasy. So for calculation questions that are very easy. So that's deviation ratio of two maximum frequencies. Modulation index is the ratio of frequency deviation to modulating signal frequency. That looks a whole lot like this, doesn't it? With one major difference, the word maximum does not appear. So it's a ratio of maximum RF frequency deviation, plus or minus 5 kilohertz, for example, to the instantaneous modulating frequency, and this will vary continuously with speech. There's another little fact here. I mentioned 29 megahertz. We'll talk more about that in a minute. 1.0 is the highest modulation index permitted at the highest modulation frequency for angle modulation. Again, angle is FM or PM, below 29 megahertz. So if we flip back, okay, if we go back a couple, so this wouldn't be legal below 29 megahertz because the index, well, it calculates the same way. Would have to be less than 1. I think we saw that. So modulation of a phase modulated emission does not vary with RF carrier frequency, just as we saw previously. And here's a calculation example, and it works exactly the same. It asks for what is the modulation index of an FM phone signal having a maximum frequency deviation, that's the RF carrier, of 3,000 hertz, either side of the carrier frequency, or 3 kilohertz, if the highest frequency is 1,000 hertz. That's 3,000 divided by 1,000, which is 3. Again, there's 4 questions. They relate to modulation index that you'll need to know. Here's a little bit more about our 29 megahertz magic. So FCC limits modulation index to a maximum of 1.0 under 29 megahertz. Well, I snipped something out of the band chart, the band plan here, showing the 10-meter band. It runs from 28 megahertz to 29.7, and here's that magic number that I talked about, 29 megahertz. So here we've clipped a little piece out of the Considerate Operator's Frequency Guide and put a link to it here. It should also be in our manual. And this describes what goes on in different parts of the 10-meter band. We've got AM, satellite downlinks, and then notice above 29 we've got repeater inputs, FM simplex, and repeater outputs. So FM is used at the upper end of 10 meters. In these areas. Now, it used to be you could never hear anything there because propagation wasn't too great. There aren't any 10-meter repeaters in our area. They're relatively rare, 10-meter FM repeaters, but with propagation being so fabulous, there's a pretty good chance you might be able to get on and even work some repeaters on 10 meters with FM.
And I've worked some DX stations on FM simplex on 29.6.
Okay, that's awesome. That's listed right here. Yep. Good. So something that you can do. Now, I put together, this gets a little bit crowded. It looks like it's readable. Oh, yeah, okay, I think you can read this. So I tried to expand these definitions a little bit to make them easier to remember. You might recall that we've had a number of people that were wishing to get 100% on their exam, so I'm trying to provide every resource I can to make that possible for you. You'd only be getting one of these questions, deviation ratio or modulation index, because they're in the same group. So here's the definition again. Deviation ratio is the ratio of maximum carrier frequency deviation to the highest audio frequency. So here we've got a ratio of maximum allowable RF deviation to the highest allowable or maximum audio frequency. So it's a ratio of allowable maximums. So typically we'd be looking at something like plus or minus 5 kilohertz, pretty standard on an FM, with a audio tone of 3,000 hertz. Why 3,000? Well, speech is usually limited in amateur radio for between 300 and 3,000. So the maximum audio frequency would be 3,000. This is the standard amount of deviation you see on most FM transceivers. There are some cases where they're narrowing that down to 2.5 in congested areas, but we'll be talking in terms of 5. So modulation index is the ratio of frequency deviation. Sounds sort of like this here, to modulating signal frequency. So what's the difference? Well, it's the word maximum. So the formulas are pretty much identical between these two, except this is referring to maximums. So deviation and maximum go together. So in this case, the RF frequency deviation is reference to the audio frequency, but not necessarily at the maximum values. And during speech, of course, the modulation index is going to be flying all over the place because speech contains lots of different audio frequencies. So the only way to make a really meaningful measurement with modulation index is to use a constant audio frequency and then measure the deviation, which makes the formulas between these work out to be exactly the same. So although the engineering definitions are different, the calculations are identical. They've changed the words here a little bit to say RF deviation over audio modulating frequency. In this case, deviation ratio, we're talking about the maximum values, and with modulation index, we're not necessarily at maximum. So a couple more tricks. How are you going to associate this? Well, I thought of a really dumb way to do it. Maybe this will be helpful to some of you. If you could consider society's worst deviants, they may wind up in a maximum security prison. Okay, so you can kind of, that might help you remember which one this is. Also for deviation ratio, this one, we'll see that when I get to the pool question, look for the word maximum. I'm trying to tie that together. So the trick is being able to understand what these two definitions are, because there's a pool question for each one of them. And then for modulation index, the correct answer is the only one referencing two frequencies, and we'll see that when we get to the pool question. So hold that thought. We'll get into another concept. Multiplexing, fascinating area. And the concept is combining more than one stream of information into one modulating signal. Got a little analogy here. I've got a box. This is a plastic box full of transistors. And what I'm going to do is take that box of transistors and put it in a shipping carton, and then I'm going to send it to California, probably because they need transistors there, I don't know. But consider these as individual audio streams or individual conversations packaged together and then sent out over RF. That's the concept of multiplexing. It's multiple streams of audio modulating a single transmitter that then goes out and gets demodulated on the far side. I'll give you some examples of that coming up. There's two flavors we'll look at. One is frequency division multiplex, and it uses multiple subcarriers, and I'll show you how that works. And then the other one is time division multiplexing, which is TDM, that interleaves two or more signals into discrete time slots. So one uses multiple subcarriers, one uses time slots. So how does that work, you're probably asking? Well, here's frequency division multiplex, the concept. So here we've got four different audio conversations going on. And the first one is happening at, let's see, do I have a bigger picture? Yeah, I got a bigger picture here. It's happening at the normal frequency that you'd be modulating a single sideband transmitter with. The audio is from, in this case, 100 hertz to 3.5 kilohertz. We usually think 300 to 3,000, but it's close enough. You get the idea. So, all right, that's in subcarrier 1, which really isn't a subcarrier. It's the base frequency of the transmitter. The next one up, we're going to mix a different audio channel, audio frequency, or different audio source with a subcarrier. In this case, a 3.5 kilohertz. And that's going to translate that audio frequency up to 4.1 to 7.5. So you can see that we've grouped one conversation here, one over there. They don't interfere with each other because they're spread apart in frequency. We've got another one that goes up another 3.5 kilohertz, another one over here. So we've got these four different subcarriers, and we'll combine those all together and use that as, remember we talked about the term baseband? Baseband is whatever it is you use to modulate a carrier with. So in this case, we've got four different subcarriers, and we're going to modulate it onto a RF carrier to send it across the world. So this concept is frequency division multiplex. Analog subcarriers, and you'll only see this in upper frequencies, UHF and above.
Does that create a very wide bandwidth?
It does. That's why it only happens on UHF and above. Yep. There's a lot of commercial products. You might have heard of StatMuxes, or the phone company used this concept to multiplex multiple channels. You've probably heard of T-carrier, T1, T3. This is the concept that all of that works under.
And
Yep.
yeah, the phone companies used it to carry normal telephone conversations over microwave. Sometimes if they got mistuned, you could start to hear somebody else's phone conversation. Mm-hmm. And then VOA, where we had microwave links from a satellite receiver site to a transmitter plant, we would use this sort of multiplexing to get various program channels to the transmitter site.
Right. It's a whole lot easier than running wires. So here's another picture. So here we've got these sub-channels or subcarriers operating. They go to a summer, which combines these together, and then it goes out on a transmit channel, transmit frequency. On the other side, on the receiver side, it comes back, and then they demultiplex it here to get the individual streams back out again. So it's a concept of heterodyning to shift up, heterodyne to shift down, then demodulate it. So this is the concept of the FedEx truck here. We put all of these little pieces into a box, we've transmitted it, sent it away, and then we're going to demultiplex it. So in context of the pool question, frequency division multiplex is two or more information streams combined into a baseband group, which then modulates the transmitter. Again, don't let the baseband group thing confuse you. It's just what we use to modulate the transmitter. That's referred to the baseband. So where do we see this? Amateur multi-carrier digital modes, phone company carrier circuits, I mentioned, cable TV, FM broadcast subcarrier, where they sell Muzak to stores and so forth. That comes out on a subcarrier. We see it with RF TV now as well. Now we're going to move on to time division multiplex. Completely different concept. This is digital. What we showed previously can all be done analog. And the concept here is that two or more signals are arranged to share discrete time slots of a data transmission. So what we're going to do is we're going to take conversation A, and we're going to take a little slice of it, and then we're going to pass it out. We're going to transmit it and pass it out. This is happening so fast, we're sampling these so quickly, that each one of these conversations appears to be completely isolated at its output. So here's a little picture of what's happening here. So here's signal 1 in red, and we're going to add green and blue. I'm going to put them each in their own time slot. So that's that concept. A little bit bigger picture of it. Here we're showing 5 conversations going on at the same time. Of course, this all has to be done digitally. So each conversation is sampled and inserted into a time slot, a digital data stream. It's also called interleaving. And it's happening so fast that the perception is that you've got your own dedicated channel, just like it was a pair of wires. And we see this in the amateur world, in D-Star. DMR uses 2 channels, some digital modes, some satellite telemetry. So this concept is used in ham radio. And then commercial usage, digital phone circuits, ISDN, of course, which is dead now. But there's a lot of application both in ham radio and in industry. But it's not something you'd be doing on HF. As somebody mentioned, it takes a lot of bandwidth.
And you must have gotten this graphic from a German website, because if you look at the pictorial on the right, where it's the red, green, and blue bars coming up, and you look at the very top, it says Schutzbander.
I didn't even notice that.
That's protection bands in German.
Yep.
They're protection time slots.
Yep, there are little spaces in between to keep them out of each other. Yeah, that's small enough I didn't even notice it. So these are the concept. Yep. And right on to some questions. So let's see if we can remember what we talked about with modulation index and so forth. What is the highest modulation index permitted at the highest modulation frequency for angle modulation below 29 megahertz?
Bravo.
It is Bravo 1.0. It was magic. That's what's magic about 29. So all of the FM activity we have on 10 meters is going to be above 29 megahertz. What is the modulation index of an FM signal? And here I hope you grabbed one of those tricks for remembering. I'll share them again if we get it wrong.
Alpha.
It is alpha. Okay, and the tricks I'll repeat here. Notice that only one of the answers references 2 frequencies. Modulation index, ratio of frequency deviation to modulation signal frequency. So if you can grab onto that as your shortcut or trick, it'll work for you. Another trick, it's the ratio of 2 frequencies, ratio of frequency and frequency. So we're trying to give you some help here to recognize these, because it's this one is a really hard one to memorize with brute force memorization. So how does the modulation index of a phase modulated emission vary with RF carrier frequency?
Delta.
It is delta, right? And this is designed into the radio. This whole concept of modulation index is something that they're engineering concepts that the pool committee wanted us to know something about. You wouldn't normally be dealing with this on your own unless you're building equipment. What is the modulation index? Oh, a calculation question. FM phone signal having maximum frequency deviation of 3,000, modulating frequency 1,000.
Alpha.
That's alpha, right?
Alpha.
Bigger divided the smaller by the smaller, or remember the formula, that works. Here's another one. Modulation index, carrier deviation plus or minus 6, the highest modulating frequency of 2 kilohertz.
Bravo.
Bravo, correct. See, this sounds hard, but it really isn't, except for remembering the definitions. What is the deviation ratio of an FM phone signal having a maximum frequency swing of plus or minus 5 if the highest modulation frequency is 3?
Delta.
Delta, right. And
Delta.
this would be the normal case, because 5 kilohertz is what you normally see with FM equipment, 2 meters, high end of 10 meters. It's usually 5 kilohertz deviation, and your highest audio frequency is usually 3 kilohertz. What is the deviation ratio? Here's another calculation. See if you can get this one. Works the same way.
Alpha.
Yeah, it's alpha.
Yeah, it's alpha. It's easy to estimate that. If you called this 7 kilohertz and this 3.5, it would be about 2, so 2.14. You don't even have to whip out your calculator for these. You're welcome. What is deviation ratio? It is B, and I kind of gave away the shortcut here. Deviation appears in the question. It appears in only one of the answers. Also, the correct answer has the word maximum in it. So that may help you with those. What is frequency division multiplexing, or FDM?
Bravo.
It is Bravo, dividing the transmitted signal into separate frequency bands that each carry a different data stream. That's the subcarrier concept that we talked about. What is digital time division multiplexing?
Bravo.
It is Bravo. 2 or more signals arranged to share discrete time slots, the data transmission. And this was just to kind of help us remember, but of course they won't be bolded on your exam. Darn it, yeah. All right, so we'll get into some more fun stuff here. Digital protocols and modes. It's just some of the things we'll talk about there. We'll be doing about half of this, maybe 2/3 of this section. We'll finish it next week. So we're going to start out by talking about the symbol rates. But before we do that, where do we find digital activity on the ham bands? Well, here's a list where you can find some stuff. The Considerate Operators Frequency Guide also provides these bits of information for you. So this is just a reference. Anybody know what radio this is?
7300.
Yep, it's a 7300, which is a really good radio for a general or extra to get started on. Well, there's some fairly advanced extras. This is all they run. There's some countries where the majority of hams are on the 7300 because it's available in their country. It's a highly recommended radio for somebody wondering where they should begin, or even stay for that matter.
Yeah, ICOM has sold over 100,000 units.
Yep. Yep. This is an SDR with knobs. We talked about SDRs previously, so this will run completely from a computer with software. You don't have to use the knobs. The display and all of the controls can be used that way, so it's a pretty cool radio. A little bit bigger picture, spectrum display, audio scope, all kinds of fun things you can do. It's got an internal sound card. For when you as you're getting into digital, here's a resource that is absolutely excellent. This is the 3rd edition, Get on the Air with HF Digital. I bought the 1st and 2nd editions when they came out, and they were kind of, I didn't really get too excited. I mean, they were a little bit helpful. This one here, they really got right, though. So they talk about some of the technologies that have been replaced, and it's definitely worth getting. They have a chapter on VARA and WinLink, which we may be getting into next week. It's a method that's used for sending packet information. There's chapters on radio teletype, or RTTY, RTTY, FT8, Whisper, and others. So if you have an interest in getting involved with any of these things, highly recommend it. I provide the Amazon links. A lot of people are Prime members, and I get free shipping and discounts. And more than anything else, I recommend finding somebody that's doing this already. Find an Elmer. So if you want to get into FT8 or radio teletype, find somebody that's doing it. Hang out with them. So some definitions. Does anybody know what bit stands for? Interesting piece of trivia. What does bit stand for? Where did that term come from? Well, it came from binary digit. Binary digit is a bit. So it's the fundamental unit of data. It's a 1 or a 0. Bit rate, as one might imagine, is the number of digital bits per second sent from one computing system to another, known as BPS, bits per second. And there's been a lot of confusion between bit rate and symbol rate. Okay, a symbol is a characteristic of the transmitted signal that represents data. A symbol can represent more than one bit. That's why these have been a little confusing, but I'll explain that in more detail. So symbol rate in a digital transmission, the rate at which the waveform changes to convey information. Well, how might that happen? Well, a waveform could shift in frequency. It could shift in level. There's a lot of ways that you can modify phase, level, tone, frequency, or a combination of them. So if you change any of those, that can be the fundamental definition of a symbol, and that can represent multiple bits. We'll share more on that as we go along, but I wanted you to see the blue text for sure. Now baud or bauds, number of symbols per second, known as the symbol rate. Now bits per second and symbols per second aren't necessarily the same thing. So relationship between symbol rate and baud, not bits per second, symbol rate and baud, they're exactly the same, just two words for the same concept. A little sidebar here. This is from Kessler as well. I thought it was really excellent. So here we've got Bob and Alice. I don't know them personally, but we'll talk about them. So Bob is working on his computer, as is Alice. They're going out to a demodulator. This is a radio, and the information is being transmitted over the air. So this is called the air link between the two transmitters, transceivers. The data link, the computers, as far as they know, they're talking to one another on a piece of wire, but they're not. They're actually talking via a radio link. But to the computer, they don't know any better. They just know that they're sending and receiving what they like. So this is a picture of the whole system. So Alice is talking to Bob, and they're both happy, trading weather and news and ham radio talk, but it's all happening through this path, through a computer, a data link, an air link, and a protocol plus a modulation technique is known as a mode. In ham terms, modes are things like CW or AM or radio teletype, some of those kinds of things. So this can happen VoIP, Skype are some technologies that are out there that can involve some of this. Now let's look at baud and bit rate examples a little bit. Here's an analogy that I found to be very helpful. We've got a person with 5 fingers. I haven't seen anybody with 6 fingers yet. So hold up one hand. This gives you one signaling event, which we'll call a symbol. So in this example, one signal event can represent 6 different states, including the closed hand. So that's 0 through 5 fingers. You might remember from some previous discussion that that you could count the number of bits that could actually be represented. I'll have this on the next slide. If we've got 5 fingers, that 2 to the 5th power is 32 bits. So we could actually represent 32 different things with just one hand and 5 fingers. So if we raise our hand once per second, that is equivalent to 1 baud symbol per second. And that would be capable of conveying 32 bits per second. Hopefully I'll make this clear on the next slide. So electronic applications, you can shift phase, you can send different tone frequencies, you can send different discrete levels. These are all ways that you can represent fingers electronically. So maybe we'll shift the phase by 45 degrees, or 90, or 270, more or less. So how would we maybe do this? So if we're in if we're at a party, it's pretty noisy, a big room, and you've got a friend across the room on the other side. So if you held up a hand with one finger, it might be a signal to say, "Bring me a Coke." And I saw Gary raising 2 fingers. He wants a Coke and a cheeseburger. So these are ways that you can represent different kinds of information by a raising of a hand and the number of fingers. But that's pretty easy to understand. But what about 32 different states? Let's look at that. If we assigned each finger a digital value, 1, 2, 4, 8, and 16, depending upon the number of fingers you hold up, if you add these all together, you wind up with 32, or 31 with a 0. So here's some examples of different numbers of fingers being held up. You notice they didn't use any impolite gestures in this example. So it'd be really hard for a person to be able to interpret this. If you raised this hand, for example, to your friend across the room, you'd have to say, let's see, he's got 3 fingers, these specific 3 fingers, that's 2 plus 4 plus 8. Okay, that's a pizza with pepperoni, cheese, and no onions. That'd be hard for a person to figure out, but it's really easy for a computer to figure out. So this is a concept of different kinds of symbols representing a different number of bits. So let's take a look at it here. There is a related pool question. A more efficient digital code can increase the data rate without increasing the bandwidth. You can kind of see that from what we've discussed so far. So data rate in bits per second is greater than the baud rate when there are more than 2 states per transition. And a transition, again, is a symbol or baud. So if we're changing states 300 times per second, we have 2 states, that's 300 bits per second. However, if we can have each change of symbol represent 4 states, or 4 bits, we can increase the bits per second to 600. And on it goes. So you might remember back in the good old days when people had telephone modems, and the coolest thing in the world is when you could take your computer, hook it to a modem, and talk to CompuServe and exchange email with somebody that's also on CompuServe. That was so cool. That was, those very early modems were 300. The first, really commercially available. The government was running 110 baud sometime before that, starting in about 1959 or so. So that was very cool. And then little by little, as time went on, technology got better and better. You can see that we climbed and climbed. And then if you got to the point of having a 56K bit modem, you were just at the top of the pack, okay? That was the latest and greatest. Most phone companies couldn't handle 56K, but they could get close to it. And the modems would have what they call a training sequence, where the one initiating the call would send out a data stream, and the other one would interpret how fast it could receive. So they'd talk to each other, and then at the fastest rate that they could both communicate, that wound up being the bit rate that was used. So bandwidth goes up, as the signal rate or baud goes up. So just another explanation of how that works, or can work. So you can have a much higher bits per second rate than you have a symbol rate or baud. Okay, we're going to continue on. Does anybody know what this is?
It's a secret.
It's a secret. It's a secret decoder ring. I don't know if that's the Little Orphan Annie decoder ring or whatever it was on the movie, but this was an example. You turn the, you'd send somebody, you give them a piece of paper that would have numbers on it, and you turn the decoder ring to the different numbers, and that would translate to the letter. So this is a secret decoder ring. And this is some teletype tape. Looking a little bit more at this coming up. So protocols and codes. I found this concept a little bit confusing, so I added some words here that I think might help. So the protocol is rules for encoding, packaging, and exchanging and decoding digital data. So here's an analogy. Just like when you meet someone for the first time, there's normally a set of rules before communication can take place. Eye contact, a smile, maybe a handshake. So that would be the proper protocol to meet somebody for the first time. There's also cultural things that you have to be very careful of, that you don't offend somebody from another culture, and you have to know what that protocol is. And in the computer world, we've got AX.25. It's a digital protocol for communicating. It's a set of rules for packaging information and sending it from one computer to another. Now, a code is rules to change information from one form to another. That's like our secret decoder ring. Letters to defined patterns. Morse code, Varicode, Baudot, and ASCII. These are all different codes. So this helped clarify it a little bit for me. Added this in there. I don't believe there's a pool question there, but it'll help you relate to the material. So here's an example. We're going to talk about variable length codes first. So in this case, we're going to talk about Morse code. Morse code is interesting because the number of code elements differs between letters. For example, an E is a single dit. Well, the reason for that is E is the most frequently used letter in the English alphabet. So if you can make the most frequently used letters be the shortest codes, the shortest transmitted Morse code, you can improve your throughput. You can have a higher average number of letters per minute, I should say. So here's some examples. So here's some short ones. E is a dit, T is a da, and here's some longer ones. Z, J, Q are letters that aren't used very often, so they get the more complex codes. In the digital side, we're going to have a diagram of this coming up in a couple of slides. The HF digital mode PSK31 uses variable length character coding. This is sending ones and zeros digitally, and it has shorter codes for the letter E and the letter A, that sort of thing. So that this is an example of variable length codes, and we're going to expand on this a little bit. So Morse code is kind of a Varicode. I put this in quotes because the concept of Varicode, of different number of code elements per letter, definitely applies to Morse, but of course Varicode wasn't invented until much, much later. So this is a concept that has been really amazing to some people. Even people who are CW operators have never seen this particular layout before. So there's a thing, like when you're in a big shopping mall, there's an arrow that says you are here to orient you on the map. Well, this one has a start here spot. Notice that the letter E, if you start here and you do one dot, you've just created an E. 2 dots, dot, dot, is an I. 3 dots is an S. So the shorter characters are the most frequently used characters. So a T is a single dash, M, O. If you get to one of these that's really obscure, like a J, that's dot, dash, 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 or it would be spoken as da, 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 da. Takes a lot longer to send that. Does anybody know what this is? Well, I'll just have to tell you then. That's a type case. A long, long time ago, when printing presses first became functional, became popular, they would use what's called a type case. And each one of these little boxes would have small lead letters. And you would put those letters together onto a device that would hold them together. Type bars, they were called. And that would form the words on that particular line. Then you'd assemble those all onto the printing press, and you could crank out printing. Now, just before leaving this slide, I would like to make the comment that please, if you're not doing Morse code, don't try to learn it this way. that would be a bad idea. You can't count dots and dashes and ever become proficient in Morse code. You need to learn the sounds of the letters as standalone units. So here's another one. So you've heard the term uppercase and lowercase. Well, here's an old type case. You can see the individual letter pieces here. It's different size boxes. In the lower part of the case, that's lowercase letters, and the capital letters are up here. This is the upper case. So now you know where those terms came from. There's a fascinating history on all of this, and I put a link here if you wanted to get into it a little bit further. So when Morse and Vail put together the Morse code, how did they decide that an E should be 1 dot? Well, they looked at a printer's type case to find the frequency of letters used in the English language and constructed their code accordingly. Now we'll move on to the PSK31. I mentioned that PSK31 was a Varicode, and that this is where the real term came from. The number of bits that are sent, and these are digital, can vary between 1 and 10. So let's take a peek here. We're going to look at the letters E, I, and O. So here's the letter E. Yeah, it looks like you can read that. Its code is 1, 1, very short. Now this is a lowercase e. What happens if we send an uppercase E? Look at the size of this code. So here's something to keep in mind. If you're going to be running PSK31, don't have your caps lock key turned on. So it'll take a lot longer to send some of these characters. You can get about 50 words per minute on average with PSK31. It's a keyboard to keyboard mode. You're using your keyboard and talking to somebody on the other end. They're seeing it on their display. They're responding with their keyboard. So that's the short characters are going to be the lowercase characters. Now let's consider the letters G and J. Notice how long those codes are. They're humongous compared to some of these short ones. But they're not used as often, so it won't slow your throughput down. So lowercase is more efficient. Make sure your caps lock key is turned off. There's a good article on Wikipedia about Varicode, but I just wanted to introduce the concept of shorter length codes for more frequently used letters, both in the CW context and the PSK31 context. Moving on to another concept, automatic link establishment. There's one pool question on this, and when I first was digging into it, I didn't know what ALE stood for, so I dug into it a bit and share some information for you here. It'll automatically determine the best frequency to use between two stations, and even alert operators when it is found. So let's look at the picture here. I don't think I've got a bigger one. Yeah, actually I think the next one is, yeah, this one's a little bit bigger. So here's two stations, and on 20 meters they have a path, okay? But on 17 meters it skips right over. So they can't hear each other on 17 meters. They can't hear each other on 40 meters, but they can hear each other on 20. So the concept of automatic link establishment, or ALE, is that they constantly scan, this technology constantly scans a list of frequencies, activating the radio when the designated call sign is received. You flip back here. Yeah, I thought I had a link. If you're interested in learning more about this, there is a link here. There's an organization that has all kinds of information, software on this protocol. So one pool question. Then moving on to gray code. This got started way before we had radio, 1878. Radio first, people were experimenting with it in the late 1800s, early 1900s. And its concept, it's a digital code that allows only one bit to change between sequential code values. Now they didn't have radio back here, but they did have automated machinery that could, very bad things could happen if it malfunctioned, if the machinery malfunctioned. So the idea was, as they increase, here's a picture of a rotary encoder, more about that in a minute. So the gray code, when you advance from decimal, here's decimal, 1, 2, 3, 4, 5, 6, 7, and forward. The gray code, you'll see, only changes by 1 bit as you go up each number. So 0, 0, 0, 0, 0, 1, okay, we added a 1. Now for decimal 2, we're going to make it 1, 1. Notice that we've only changed 1 bit. Now when we get to 3, we've dropped this 1 to a 0. So again, we've only changed 1 bit to represent the number 3. Well, what happens in binary? In binary, which we're more used to seeing, we go from 0 to 1 to 1, 0. Okay, 2 things changed here. We flipped the 0 and the 1, and on down the list. So gray code would allow you to only have 1 change per increment in what was being input. This allows, this would allow the machinery to detect some kinds of errors. If they saw something that wasn't a 1-bit change, they knew something would be wrong and could shut down. In more modern terms, maybe that would prevent a missile from launching. They didn't have that back here, though. In ham radio, we have rotary encoders. Your VFO knob on your radio, you'll notice it goes around and around and around, and it never stops. Well, this is a picture of what that is, what could be happening there. We're shining light through a code wheel. Then we've got some photo photo detectors on the other side that are reading the codes. And as you turn, this would be connected to your knob. As you turn this, you'd be advancing your frequency. The radio would know what to do with that information. Here's a little bit bigger picture. You can see 1 bit changing per increment of a control. There's a little picture of a rotary encoder, a light source, and a code wheel that's turning. Now we'll move on to another concept. Here we've got fixed length codes. ASCII came on the scene around 1960. American Standard Code for Information Interchange. And there's a collection of concepts here that we see in ham radio. So 1s and 0s can be concatenated into bytes, usually 8 bits long. The far left would be the most significant bit, least significant bit, and then here are the individual bits that represent the letter A. So if this is one byte, you can combine these, byte 1, byte 2, byte 3, into a long string of things, that we do with packet radio, so that every one of these letters becomes 8 bits, which then can be concatenated into packets, can have a header with address information, the payload, as it's called, in the middle, and then parity. Parity, the concept of parity is that using a number of techniques, you can determine if the packet was received correctly. We'll talk more about this next week. So header handles addressing, parity added for error detection. That's ASCII. Moving on to this handsome devil here, Emile Baudot. He lived a long time ago, 1845-ish. That's back when they were using teleprinters, again before radio. like a typewriter looking instrument. And notice that we're using 5 bits here, and I've put 5 bits in blue. There's a pool question that's really complicated, but if you can just remember the number 5, you'll recognize the answer immediately. So let's have a look at what's going on here. This would be a tape. I used to show this in class. I had some that I got from a Hamfest, but I couldn't find it for this class, so we'll just look at the picture. So these little dots in the middle, these are sprocket holes. So you could put this, you could pre-record a message, you put it into a machine that pulls this tape through, and then it's reading these punches. Remember the hanging chads from the Florida election? Well, this is something that would be similar to that. Hopefully you've got nice clean punches through the tape. So let's look at the letter D. And the bits, the code elements, 1, 2, 3, 4, 5. The letter D, you could translate this to 1, 0, 0, 1, 0 for the letter D. Now notice, because there's 5 bits, 2 to the 5th power is 32. So we've got a problem right away. We've got 26 letters in the English alphabet, and then we've got 10 numbers. Well, we have just exceeded our 32. So what are we going to do? They came up with an ingenious solution. They have a shift code that when this is sent, it tells the receiving end that, okay, I'm going to switch to figures mode now. So we've got letters going across the top. And then if we send the character that switches it to figures, now this line is used. So we got all of the numbers and some symbols that can be used. So that'll increase us up to 64 possible different states that we can represent. So we saw on our hand, the fingers could represent 2 to the 5th power, which we have here in Baudot for either the upper level characters or the lower level, not uppercase and lowercase. So how does this work? Well, here we've got our tape again. So we're going to be using, in radio terms, the original teletype machines used current loops, so it'd be a high level of current or a low level of current that would symbolize a 1 or a 0. In radio, we use tones, known as a mark and a space tone. And that has an interesting history too. In the early days of Morse code, it was conceived as a code where a pen would come down on a moving tape and make a mark. So when you're sending a dash, for example, the pen would come down and transcribe a line on the paper, which would be a mark. Okay? When the pen lifted, that would be a space. And so that concept we still have with us today in terms of mark and space tones. We're going to be using these as tones transmitted on single sideband, and they're typically 2125 hertz and 2295 hertz for mark and space. So let's see how we're going to apply those. Normally the mark tone is being sent continuously. When it switches from mark to space, that we're going to interpret as a start symbol. So the receiving end is going to tell itself, okay, I'm receiving continuous mark. All right, we just switched to space. That's my start symbol. I'm going to pay very close attention to the next 5 things that happen in these bits, little time samples. So bit 0, bit 1, 2, 3, and 4. So we've got our start symbol, and now the receiving side is going to start paying attention. The next one goes to mark. So that's going to go high. So that represents a 1. Then it goes low and stays low for 2 spaces. So we've just sent 1, 0, 0. Then it goes high. There's a 1, a 0. And then a stop symbol. So that's 5. 1, 2, 3, 4, 5. So it thinks that it's complete, and that's confirmed with the transmission of what's called a stop symbol. That's about 1.5 time periods of one of these. and then another start symbol comes, and the next character comes. So that's the basic idea of how Baudot works. Radio teletype, this is how that works. Some people call radio teletype, when they hear it on the air, they equate it to a diddle-diddle sound, and that's kind of what it sounds like. And you can see where radio teletype would appear on the band in the Considerate Operator's Guide. RTTY isn't used very much, with one major exception. There's RTTY contests, and the people that do this are crazy. I've only done RTTY maybe one time. There's a once per week half-hour session where you can get on and test your equipment, and I did that once and made a few RTTY contacts, but I haven't done any RTTY contesting. But there's people that have thousands of contacts over a year with RTTY. It's extremely popular for that purpose. So here we'll switch back to ASCII for a minute, and this is an ASCII table. There's normally 7 bits, which would represent 128 characters, that would let you represent everything that's shown on the table here. There's a Wikipedia article that goes into much more detail. There's something called extended ASCII, where you can use 8 bits, and that gives you 256 characters. So we can see the representation of what the control characters do, and what the letters, the letters and numbers, uppercase and lowercase, all represented in the in this table. And these can be sent at different speeds, 4,800 bits per second, 400, so forth. Serial ports on computers can go, or typically go up to about 115, 200. So if you want a lot more information about this, if you Google on the word modem, you can get the history of how all of this came about. And here's a link to a Wikipedia article. These links will work in the PDF that Gary will be sending tomorrow. All right, so with both ASCII and Baudot, we've got start bits. Well, no, we don't have it for both, but the concept of start bits, parity applies to ASCII, and stop bits applies to both. Transmissions are asynchronous. That means that they don't depend on any timing on one end or the other. They depend upon a start bit, so you can start it at any time, built in to the protocol. For ASCII, an advantage of using parity is that some types of errors can be detected. So you may have heard of even and odd parity. So if the number of ones in the byte is even, there's 2 or 4 or 6, you would put a 1 as a parity bit. Odd parity would be just the opposite. If you're using odd parity, you'd set the parity bit if the number of bits in the byte were an odd number. No parity is most common. Why do you care about any of this? A lot of times when you're configuring your computer to your radio, you have to set up these parameters, the number of bits, the number of start bits, the number of stop bits. So you will run into this. In the good old days, there was always 2 stops for mechanical teleprinters because it took them time to react. And today, the stop bits are pretty much always 1 for mechanical or for electronic. A little bit more on stop bits. 7 or 8 bits per character for ASCII, 5 bits for Baudot. There's our number 5 again. The 7 bits would be the 256, or the 128 characters. The 8 bits, or extended ASCII, would give you double that. And here's some differences, and I highlighted the elements that appear in blue are all pool questions. So they ask about differences between Baudot, which is radio teletype, and the amateur implementation, and ASCII. So with Baudot, we've got 5 bits per character, and it uses 2 characters as letters, figures, shift codes. So you can go between numbers and letters. There's some other facts, but it's only the blue ones that show up as pool questions. With ASCII, it's 7 or 8 bits per character. There's no letters or figures shift code needed because there's enough elements in the 128 or 256 to cover them all. An advantage of ASCII is it can send upper and lower case text. Parity bits can detect some types of errors. So here's a side-by-side comparison between the two with the ones that will appear in the pool. Speaking of the pool, what is the definition of symbol rate in a digital transmission? We'll go through these questions, then we'll take our break. What is the definition of symbol rate in a digital transmission?
Charlie.
It is Charlie. Yeah, something is changing in the waveform to convey information, which could represent multiple bits. How can data rate be increased without increasing bandwidth?
Charlie.
Charlie, more efficient code, more bits represented per symbol. What is the relationship between symbol rate and baud?
Alpha.
Alpha.
They're exactly the same. It might not be the same as the bits per second. How do ALE stations establish contact? Automatic link and establishment.
Alpha.
Alpha.
It is alpha. ALE constantly scans a list of frequencies, activating the radio when the designated call sign is received. And you'll notice, again, in the considerate operator's frequency guide, there's frequencies designated for automatic operation. That's where these would be transmitting. Which of the following HF digital modes use variable length character coding?
Delta.
Delta, PSK31, uses Varicode. What is the advantage of including parity bits in ASCII characters?
Delta.
Delta.
Delta, some types of errors can be detected. If you've got multiple errors in the data stream, then you don't have a clue what's going on, but some kinds of errors can be detected. All right, and here we're going to use our magic number. What are some of the differences between the Baudot digital code and ASCII? Tons of words here, but one thing in particular will get it for you. It is Baker. Yep, it's the 5 data bits. And I gave you a table with differences between the two, but the 5 will save you a whole bunch of time. What is one advantage of using ASCII for data? Excuse me. What is one advantage of using ASCII code for data communications?
Charlie.
It is Charlie, possible to transmit uppercase and lowercase, because with 7-bit ASCII, you've got 256 or 128 characters, which includes all of the upper and lowercase letters and symbols. Which digital code allows 1 bit to change between sequential code values?
Delta.
Delta.
It is Delta, that's the gray code. And then we're going to get into digital modes after our break. So we've gone a little bit longer than an hour, but you only get 5 minutes for your break. No extra credit for that. So go do something fun for 5 minutes. Get up and wander around, get a drink or whatever. we're back. I hope everybody did something fun during their break, and I hope everybody came back. I can't tell, I'm not counting noses, but we're going to continue on. We're in digital modes as the next section that we're going to jump into. Several topics here. Now, modulation common below 30 megahertz, kind of an HF focus here. We've got several. Got PSK 31 that we've talked about already, up to 50 words per minute. It's an average. How much bandwidth does it consume? Only 37.5 hertz. Morse code at 13 words per minute consumes about 52 hertz. You'd think that Morse, if it's just a single carrier, it would be narrower than that, but because you're turning the carrier on and off, you're disrupting the signal, and it's causing that disturbance in the RF is causing bandwidth to exceed 0. There's an analogy that I like using. It's a little bowl of water and your finger, and if you tap your finger on the top of the bowl of water, you'll make waves. And the faster you tap your finger, the more disruption there's going to be there. And that represents bandwidth in the RF world. We'll be coming back to that. Single sideband voice, up to 120 words per minute. We can talk pretty fast. And the bandwidth is much, much broader, 300 hertz for single sideband. For AM, it would be double that, 6 kilohertz. So think about this for a minute. Morse code at about 50 hertz. You can imagine how many signals you can fit in the space of one single sideband channel. 3,000 divided by 50. That's a bunch. So there's one kind of disjointed pool question that fits here. Frequency shift keying, FSK. We'll be talking more about that. You're actually shifting frequency that's like between the mark and space tones, is a type of modulation that used for data emissions below 30 megahertz. It can be used elsewhere as well, but typically you'll see it on HF. Something that'll come up in a question. So PSK uses phase shift keying. PSK is phase shift keying, and radio teletype uses frequency shift keying, the mark and space that we were talking about earlier. So on your radio, on your transceiver, you'll probably have it'll either be buttons on the front of your radio, or this is a picture of, I think it's my 7610, where you touch the mode. If I touch where it says CW, it'll bring up this screen and allow me to pick a different mode to put the transceiver into. But every transceiver will give you a means to switch between modes. So I'll talk about frequency shift keying, like for radio teletype. Do different tones shifting from one frequency to another. And here's a spectrum display. You can actually see the individual tones. Strong signal, 2 tones. This would probably be during a radio contest. Rapidly changing tones are called mark and space. The diddle-diddle sound that I mentioned, if you listen to it. Space represents 0, mark represents 1. And they're typically spaced about 170 hertz apart. I mentioned you don't need to know these frequencies. Mark and space are usually 2125 and 2295, separated by 170 hertz. FL Digi and MMTTY, various other kinds of modes use these concepts. So a little expansion on the radio teletype. Standard tones, mark and space, separation of 170 hertz. Back in the good old days, when the TNC's terminal node controllers first came out, the PK232 was extremely popular with hams when some of these digital modes first began. That used 200 hertz spacing, which is considered non-standard, but it's close enough to the 170 that we use today where they would still work. So let's consider how these things are generated. Oh, before I do that, I mentioned that there's a 30-minute This runs once a week. I think it's on Wednesday night. So if you want to play around with radio teletype, you can set up your equipment and go on the air. You go to this site and it'll tell you what the frequencies and times are, and you can see how many people you can talk to in half an hour. It's a real good exercise for getting going. So how do we generate frequency shift keying, like for radio teletype? So there's two methods. There's direct FSK and audio FSK. So what we have here is a computer and a keyboard, of course. And it will, there's a control line that goes directly between your computer and the radio that's going high and low. It's sending digital data. That is interpreted by the circuitry in the radio to directly modulate the variable frequency oscillator. So the reason it's called direct FSK is because you're directly shifting your radio's oscillator by 170 hertz. So that's direct FSK. Audio FSK, different concept. What we're using is a sound card either in a computer or in your transceiver, and then we're going to transmit those audio tones as upper sideband, single sideband. That's audio FSK. So either we're using a feature of the radio to slightly shift the VFO, or we're sending audio tones via single sideband, and on the receiving side, they they sound exactly the same. Now, there's some controversy in ham circles about which one is better. So some people say direct FSK is better. Some people prefer audio FSK. I guess it boils down to if your radio has the ability to use direct FSK. Not all do. All modern transceivers do. The slight disadvantage for audio FSK is you've got to make sure that the levels are set just right. When audio FSK is set up correctly, they're absolutely identical on the receive side. I would prefer direct FSK because it's less fooling around with all of these levels and sound cards, but they both work. Now, there's a poll question, difference between direct FSK and audio FSK. Direct FSK modulates the transmitter VFO. So it's directly changing the frequency rather than sending audio tones. So that's the concept. There used to be some pool questions on this material. There aren't any more, but I thought it was worth keeping in the presentation because when you're operating a mode that's using some kind of shifted keying, the software that you're using will normally have some kind of a display like this, a tuning display. And this is what you want. The mark and space tones should appear this way. If it's off, then you get one of these. So diagram A shows proper tuning and equal levels of mark and space tones. This is happy. Diagram B shows mistuning and one weak tone. Notice one tone is smaller than the other one. Might be a filter issue or selective fading in the ionosphere. And then C, which is the ugliest one, shows mistuning or transmitted tone spacing not accurate. That should normally be 170 hertz apart. One of these is not. And here's an amazing concept. Selective fading is indicated when one of the ellipses suddenly disappears. Now, this would be due to one of the signals not making it through the ionosphere, and they're only 170 hertz apart. Well, that's a heck of a filter, but the ionosphere can do some weird things like that. So the tuning indicator you get in your software can help you set up your system. So I'd share that if you want to get into it. Now, bandwidth, there's a document, SM.1138-3, our book says -2, but 3 is the current version. This is available as a PDF, so you can have your very own copy. However, I don't recommend that you read this unless you're trying to put yourself to sleep. It's pretty technical and pretty heavy, but it's the basis for what we're going to see in the next few slides. So simplified, and Kessler simplified it this way: bandwidth versus symbol rate. Okay, So bandwidth simplified is symbol rate, how many symbols per second you're sending, times something called the shape factor. With Morse code, it would be how suddenly the rise and fall times are occurring, or it would be the shape of the data pulses. So there's, for different kinds of transmissions or different kinds of modes, there's a different shape factor. So how wide is the signal going to be? Well, it's symbol rate times the shape factor. Bandwidth equals B times K. And Kessler notes there's no free lunch when it comes to bandwidth. Faster baud or symbol rates means more bandwidth is consumed. We're going to see a couple of formulas in the book that help us calculate some of these for different kinds of modes. So for FSK or AFSK bandwidth, here's the formula, K times shift plus B, where K is 1.2 and B is baud. Well, you can memorize that formula and try to figure out how to apply it if you care to, but I'm going to give you some shortcuts that'll let you do these without having to go through that pain. It's nice to know where it comes from, but I'll help you do it in a simpler fashion. So the bandwidth of a, this is a pool question, the bandwidth of a 4800 hertz frequency shift, 9600 baud bandwidth, ASCII FM transmission, a few extra words that you don't really need there. The way it applies to the formula is 1.2, K is 1.2, times the shift, 4800 hertz shift, plus the baud. You plug these into the formula, you get 15.36 kilohertz. So what's the easy way to do that? So the easiest way is to choose the answer closest to shift plus baud. It won't be exact, but the number that's closest to that will be the right answer. So shift plus baud, 4800 plus 9600 equals 14.4, which is real close to 15.36. So that's a lot easier than trying to remember the formula. There used to be a couple of these in the pool. This is the only one now. And there's a little chart down here. These numbers are meaningless and don't apply to what we're doing here, but the concept is shown nicely. The bandwidth is considered the distance that the signal occupies. So in this case, that 15.36 kilohertz would be this distance here. And then it should be way down from that on either side. A narrower mode, like CW, would be closer to a single spike in the middle. So that's the concept. So here's a thought question. If the formula wants a value for baud, how can we handle bandwidth for CW, which is rated in words per minute? So think about that for a second. In order to calculate bandwidth for a CW signal, well, the words per minute are going to change, certainly. And we saw previously that shaping factor came into play. So let's see how we're going to answer that question. Okay, the factors that affect the bandwidth of a transmitted CW signal are the keying speed and shape factor. So we saw the shape factor in the formula a couple slides ago. And in CW, that's referring to the rise and fall time of the carrier turning on and turning off. There's a standard word. So words per minute. Well, a word is normally considered to be 5 characters. But there's a standard word that is used to compare bandwidth and performance in CW, and that is the word Paris, P-A-R-I-S. That's 5 letters. And we'll see on the next slide that the way Paris is constructed, it translates to 0.8 baud. So the way that we would calculate CW bandwidth, word per minute times 8 would give you baud, times K, which is the shaping factor, and then K is between 3 and 5, reflecting the abruptness of the keying waveform. A more abrupt waveform would give you closer to 5. And the example they give us in the pool uses 5. So the approximate bandwidth of a 13 word per minute CW signal would be the bandwidth. Okay, we're looking for the bandwidth. So 13 times 0.8, that gives us the baud, times 5, which is the shaping factor that we're going to be using for CW, equals 52 hertz. So again, a little bit of math stuff here and a formula and all of that. But for the exam, I'll give you another shortcut. It's just the words per minute times 4, which happens to work out to exactly 52. So this is the background of why it is what it is, and here's a shortcut. So what if we sent the word Paris 13 times in 1 minute? Well, we'd be sending at a rate of 13 words per minute. And just for fun, for those who don't have any idea what 13 words per minute CW, I'm going to send the word Paris 3 times in a row here. We tested this earlier and hopefully it'll work. I got to turn this off first. So for those of you that are interested in learning CW, and you can be a ham your entire life and never do CW. I'm not saying that a real ham does CW or any foolishness like that, but if you do want to get into CW, you're doing it right now, 13 words per minute is kind of a slow rate. You don't hear that on the air very much, but for things like Parks on the Air and some of the slower 1 hour contests, it's very possible to work those in the range of 15, 16 words per minute. So it's not, you don't need to be a lot faster than this to be functional in CW. You can certainly carry on reg-chew QSOs at that speed. You'll want to get a little faster than that. The contest that I just worked this past weekend, I got about a little over 400 contacts, the CQ Worldwide DX contest. I got 406, I think, contacts in about 10 hours. It's a 48-hour contest. Gary's clapping. You should hear, he got over 1 million points on this single sideband one a couple of weeks ago, so you can clap for him too. But if you are interested in getting into that, it is a challenging and fun way. I have a friend who was worried about mental decline, older fella, and he felt like, and there's been some studies that prove this, that CW will help you slow down mental decline. So that may be a motivation to get into it, in addition to it just being fun. Now, I had to do CW when I first got licensed as a novice in the late 60s. You had to do 5 words per minute, and then you had to do 13 words per minute if you wanted to upgrade to the general class, to get a lot more privileges, and then 20 words per minute for extra. Well, there's no requirement for code today at all, but if you were involved with it back then, it'll come back. It's like riding a bicycle, and it is fun. And I think I heard Gary say one time that, that one advantage of using the CW mode is that the person on the other end doesn't know if you're a dog. They don't, you remember that, Gary? Or if you're a man or a woman, or if, you know, they can't hear a foreign accent.
I remember that one, no.
Oh, okay, yeah, I thought I heard that from you. So at any rate, CW can be a lot of fun. You don't have to use it. Another advantage of CW, if you're doing summits on the air where you've got to pack radio equipment up to a high, what they call a prominence, not really a mountain, you know, where you've got to do rock climbing and stuff, but high hills and so forth. The highest point in your state is probably a summit. It's much easier to pack lightweight, you know, 5 watt QRP radio as versus something that's 100 watts or more. So CW is by far the most popular mode for doing summits on the air. So there's some motivations for wanting to do that. And there's a couple of organizations that do a wonderful job of training. I meant to put the links in here, but maybe I'll put them in next week for you. Their CW ops, and Long Island CW Club do a fabulous job of training new people in CW. So at any rate, you now know what 13 words per minute sounds like. So this is the word that we talked about, Paris. So how is CW constructed? Well, the letter P is da-da-da-dit. The dit is the fundamental timing unit in terms of CW elements. So we've got one timing element here. This is a dit, and then a space, same length of time, and then a dash is 3 dits. Space, 3 dits, space, and a single dit. So the letter P, da-da-da-dit, all right? So, and then the inner character spacing is the equivalent of 1 dit space. There's 3 spaces between letters, and then there's 7 spaces between words. So if we take the word Paris, it's 5 letters, it consumes a space of 50 time periods. So the little comment here about how that translates to baud. 50 dit lengths for the word Paris plus the following space. The dit is the symbol, so that's 50 symbols per word. 1 word per minute is 50 symbols in 60 seconds, works out to 0.83 symbols per second, or 0.83 baud. That's how they came up with that number. But I wanted to show this just so you'd see the timing relationship in CW. And again, if you sent 13 of these in 1 minute, that would be a code speed of 13 words per minute. Phase shift keying, PSK 31, is when it first came out, there's a Brit that came up with it, Peter Martinez, in late 1998. And it's a keyboard-to-keyboard mode where you would send somebody a message here. The person on the other side would be reading it on their computer monitor, and they would reply using their keyboard back to you. So it's a keyboard-to-keyboard mode, and it just took ham radio by storm when it came out, because they'd never had anything quite like this before, other than maybe radio teletype. That this was all centered around computer and sound cards. So the bandwidth for PSK 31, it turns out to be 31.25. Notice the name of the mode, PSK 31. Bandwidth happens to be 31. Here's the formula. It's one of the narrowest HF digital modes. There's another mode called FT9, but it's really not used. I'm not sure why, but that's less than 14 hertz. So there are some very narrow modes. Now, I'm going to have a couple diagrams to explain why these next couple of points are true. To minimize bandwidth, and we're talking phase shift keying, PSK 31, the phase of a PSK signal should be changed at the 0 crossing of the RF signal. I'll have a picture. The use of sinusoidal data pulses minimizes the bandwidth of a PSK signal. And I'll show you why. And there's many variations. PSK 31 was what initially came out, but there's another one that's faster, quadrature PSK 63, and these are all different variations on PSK 31 that some people are using. So here's the pictures that I promised. So to minimize bandwidth, you change phase at the 0 crossing point. You might remember when you key a single sideband transmitter, no transmitted RF leaves your transmitter until you supply some audio, because the carrier is suppressed, and therefore when you key the transmitter, nothing happens unless you speak. So by changing by changing phases at the 0 crossing point, you have less disruption of the RF signal. Again, tapping your finger in a bowl of water happens a lot less if you're using the 0 crossing. So how does this work? Well, here's a space of digital 1. Now we're going to change phase by 180 degrees and then leave it there for 2 time spaces. So we're sent 1, 0, 0. I'm going to change phase again, leave it that way for 2 time spaces. And you can see, well, in this case, we're sending 1, 0, 0, 1, 1, 0, 1, 0, 1. How many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Not that that's important. In the sinusoidal data pulses, it's the same idea. We have less disruption to the RF if we can shape these pulses with gradual rise and fall times. And that these two factors contributed to it only having a bandwidth of 31 hertz. So let me flip back, see it in the context of the pool questions, and hopefully these make more sense now. CW, all right, some factors here, and then we'll do some questions. So this represents a keying of a transmitter for a short period of time, and what we're leading to is fast rise times equals something called key clicks, which are bad. So this looks like a square wave, right? You key your transmitter, this is the RF that gets sent.
Turn on your laser pointer, can't see it.
Thank you. Here we go. Yep. So a very fast rise time, fall time. This is with no shaping. All right. Now with proper shaping, where we round off, we increase the rise time and the fall time. This gets rid of those rapid changes. You may remember that a square wave is the fundamental frequency in all of the odd harmonics. Well, when you key your, when you're sending CW, you don't want to be sending a whole bunch of garbage due to these rise and fall times. So the primary effect of extremely short rise or fall times is the generation of key clicks. Why do they call them key clicks? Because that's sort of what it sounds like. If you're listening to somebody on the air that has this issue, it'll actually be clicky at the beginning and the end of the sent CW character, or element, I should say. You can actually see this on a spectrum display where normally you would expect a CW signal to be just a single blip going up, but you'll see one with a bunch of little spikes on each side. I noticed that in the contest this past weekend. Some people had that. In some transceivers, you can actually adjust the rise and fall times of your CW signal, which might
Back
be,
in the novice days, you heard key clicks a lot.
Oh, a lot, yeah, yeah. Exactly, because they weren't very sophisticated about this. So we saw that. The most common method of reducing key clicks is to increase keying waveform rise and fall times. Now this pool question, a lot of people get wrong because they get it backwards. So let's take this apart a little bit. To reduce key clicks, we want to increase the keying waveform rise and fall times. That means we want it to take longer from key down to when RF goes out. So we're increasing the keying wave rise time, and on the other end we're bringing it down gradually as well. So be careful not to get this one backwards. So any QST article that you read where they're reviewing a radio, they will normally give you waveforms of CW transmission output. So this would represent the key down, key up, and this is how the RF is following it. Takes a few milliseconds before, when you press your CW key down, takes just a few milliseconds before the RF comes up, and then when you let go, it takes just a very few milliseconds for it to come back down. But notice these smooth rise and fall times. So this would be a good example. You don't want it to look like this. You'll see those for every product review. All right, a few questions and we'll be done. What is the approximate bandwidth of a 13 word per minute international Morse code transmission?
C.
Charlie.
Yep. You can do the formula or do 4 times 13, you get 52. What factors affect the bandwidth of a transmitted CW signal?
Charlie.
Charlie, keying speed and shape factor, which refers to the rise and fall times. What is the primary effect of extremely short rise or fall times on a CW signal?
Charlie.
Charlie, generation of key clicks, yep. I was going to wait you guys out. Okay, what is the most common method of reducing key clicks? And this is the one that you'll want to get backwards. So think about this.
Alpha.
It is alpha. Yep. Which of the following types of modulation is used for data emissions below 30 megahertz? A lot of them actually, but there's one in particular that we talked about tonight.
Baker.
Yeah, Baker frequency shift keying would be like used in radio teletype. I keep going back to that because we talked about how that worked. What is the difference between direct FSK and audio FSK?
Alpha.
Right, direct FSK modulates the transmitter VFO, usually by switching a capacitor in and out. What is the bandwidth of a 4800 hertz frequency shift 9600 baud ASCII FM transmission?
Alpha.
You might remember it from our discussion, but the easiest way to get to that, if you don't remember, is just add these two numbers. That's not what the formula says, but it'll get you close. Why should the phase of a PSK signal be changed at the zero crossing of the RF signal?
Alpha.
Alpha, to minimize the bandwidth. We're not disturbing the RF as much that way. What technique minimizes the bandwidth of a PSK31 signal?
Charlie.
As Charlie used the use of sinusoidal data pulses. Nice slow rise and fall times on the pulses. And guess what? We're finished for tonight. Isn't that wonderful? A little bit early. We can get into class chat. We'll be finishing the chapter next week, so I'll be sending an email, but you'll be reading from page 811 to the end of the chapter. And I'll be sharing the Kessler videos for the repeat of 8.2, which we only covered part of, and all of it 8.3. 8.3 is primarily about amateur TV. It's a very interesting topic area. It's a niche area of ham radio. It's only used in bigger cities, but it might be of interest to you. So that's it for tonight. And we'll do our class chat thing now. So you can start that, Gary, if you'd like.
Any questions, comments?
Need to super source us. Oh, there we are. Okay.
You wore them out again, Dave.
I guess so. I think I wore me out too. I feel my voice starting to fade out a little bit. But interesting stuff, and if for no other reason, it'll help you with the pool questions. Some of it's very practical, though. Very practical. Hopefully, we connected enough theory so you know why the right answers are the right answers, and you'll be able to use some of this going forward in your ham radio career, as we like to call it.
All the links will be available tomorrow when you send out your email.
Yes.
Exactly, yes.
They will. Yep. And I tested all of the links and updated them if needed, and they all work.
You'll get a PDF of Dave's presentation. There's also going to be, the link is in the description box for the YouTube video. And when you open up the PDF, the links will be active.
Yep.
Thank you.
You bet.
You betcha.
Yeah. Another great session.
Let's
All right.
let them go home.
Yep.
Oh, they're already home.
Yeah, exactly.
Thanks, y'all.
Yep.
We will see you
Next week.
next week. 73.
Yep.